This question is from Physics chapter Electric Potential. In this question, it is given that 2 point charges Q and minus Q are located at 0, 0, minus A and 0, 0, A respectively. We have to depict the equipotential surface due to this arrangement, and also we have to find the work done in moving a small test charge Q0 from 1 to 0. So let's solve the first part of the question. So here we have to draw the equipotential surface. So if we have a 2 point charges, let's take this as plus Q and here it is minus Q. And the position of plus Q is 0, 0, minus A. So you know that this is your x-axis, y-axis and z-axis. So minus A lies on the z-axis. Similarly, for charge minus Q, 0, 0, A. We can name it as point A. This is our point A and here is point B. We can join this and this is the representation of z-axis. Because these points are lying on the distance is basically due to the difference in the z-axis. Here we take as origin. This is the reference where the coordinate is 0, 0, 0. Now the distance of OA along the z-axis is minus A and this is plus A. So basically you can say that this system looks like the electric dipole. This system looks like the electric dipole because they have same charge but different magnitude, and also the distance are equally distributed from the center. So we can say that it looks like electric dipole. This is electric dipole. Now we have to draw the equipotential surface on it. So before we draw the equipotentials, better we can draw the electric field lines over it. So electric field lines will always move from positive charge to negative charge. So it will be drawn like this way. It's infinite lines. So we try few of it. And now based on that, if we have to make the equipotential surfaces, we will notice that the equipotential surface is actually more inclined between the positive and negative, means it will be something like this. Similarly on charge minus Q, so it will form something like this. Why it happens? The reason is clear. If you see between A and B, the electric field lines are more dense. They are very much near to each other. Equipotential surface will be more near towards the point A and same way towards the point B. But when it is going away, then this gap starts increasing. So by this way, we can say that this is the equipotential surface of this arrangement. Now in the second part, we have to find the work done when we have any small test charge Q0 from the point A, 0, 0 to 0, 0, 0. So here you see this A actually represents the x-axis, and this is y and this is z. So actually the test charge is moving from one unit from the x-axis to the center. So here if you have, this is the center, you can assume that this is the x-axis and here somewhere is the test charge. This is the test charge Q0 and its coordinate is 1, 0, 0. We have to find how much work we have to do when we move it from the point C to the point O. So we know that in this case work is equal to V into Q. So if we have to find the work, we need to first find the potential difference. So V is equal to Vc minus Vo. So potential at Vc is equal to the potential due to the charge plus Q because of this charge, and potential due to the charge minus Q. Potential of a point charge V is equal to kq by r. So we substitute the value for V plus Q. It's k plus Q by, what is the R? AC. this distance we have to find, this distance. To find the distance of RAC, we can use the formula root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square, and we substitute the values. So here in this case, this is our x2, this is the x1, y1, y2, z1 and z2. So based on that, if we substitute the value, it will be equal to 1 minus 0 square plus 0 minus 0 square plus 0 minus minus a square. So it's equal to root of 1 square plus a square. So same way, we substitute the value here for the minus q. So minus q will be k minus q by rbc. So this value we got it, kq by root of 1 square plus a square. If we find the value of bc, this value, if we find r of bc is equal to root of 1 minus 0 square plus 0 minus 0 square plus 0 minus a square. So it is equal to root of 1 square plus a square. So we substitute it here, minus kq by root of 1 square plus a square. So what is the value of the potential at C? It is equal to kq by root of 1 square plus k square minus kq by root of 1 square plus a square. Now both are same, so they can be cancelled. So based on that, we say that potential at C is equal to 0. Similarly, we have to find the potential at O, means when the charge body reach at point O. So what is the distance of AO? It's equal to minus A, and this is plus A. So we can substitute VO is equal to potential due to the positive charge at point AO minus potential due to the negative charge at point OC. So here we say KQ by RAO minus of minus KQ by ROB. So this is equal to KQ by minus A plus KQ by plus A. So this again, these two gets cancelled. So here we say that VO is equal to 0. Now if we substitute the value, both VC it was 0 and VO is also 0. So the potential value will be equal to 0. Now we have to find the work. So work is equal to potential into charge. So potential is 0. If you multiply with Q naught, so the work done will also be 0. So here for the B part, we can say that net work done is 0. This is the answer of this question.